Let us talk about this problem. We are given a number n. We need to count how many bits are set in binary representation of n. For example, if n is 5, the binary representation of 5 is going to be 101, and before that we have everything 0, right? So how many set bits we have? We have 2 set bits, that's why our output is 2. If n is 7, the last 3 bits of binary representation are going to be 111, and before that we have every bit is 0. So how many bits are set? 3. N is 13, the last 4 bits are 1101, right? And before that we have everything 0. So how many bits we have set? 3. Now please pause this video and try to write down a function that takes n as input and returns count of set bits in the given number. Let's first talk about a naive solution to solve the problem. The idea of the solution is simple. We traverse from the last bit to the most significant bit. What is MSB or most significant bit? It's the leftmost set bit, right? If you look from this side, the leftmost set bit is your most significant bit. So you begin from here, the last bit, and for every bit you check whether it is set or not. If it is set, you increment the result. Your result is initially 0. Now how do we traverse through all the bits? And how do we check whether a bit is set or not? See, for the last bit, it is very easy to check whether it is set or not. What you can do is, if n% 2 is not equal to 0, or you can say if it's equal to 1, then the last bit is set. In that case, you can increment the result. But that is only for the last bit. Now, how do we check for other bits? See, what we can do is, we can move every bit to the last position one by one. So what I do is, I do n equal to n by 2 in every iteration. And if you're programming in Python, then we can do n equal to n by 2. Floor division basically we want to do. In Python this, and C++ and Java and this. So with this operation, I can actually move every bit to the last position, and then I can check whether it is set or not, right? Now I have given you enough hints. I have given you this hint that how do you traverse through all the bits? You will move every bit to the last position. And when would you stop? When this bit moves to the last position, right? And after that you will have the value 0 after you move this bit again and try to move the bit before it, n will become 0, right? And how do you check whether the last bit is set or not? This operation. There is a better expression than this. You can also do if n and 1 is not equal to 0, right? With this, you're using bitwise operators which are faster than the %2 operator, right? So this is the idea. Please pause this video and write down the complete solution yourself. Here is our implementation of the naive method. What we are doing here is, we are checking whether the last bit is set or not. If the last bit is set, we increment the result. Then we move the second last bit position to the last bit position, right? So if you see this example, we have n is equal to 5, whose binary representation is this. We initialize result as 0. And in the first iteration, what will happen? We'll check whether the last bit is set or not by checking whether the number is even or odd. If we divide by 2 and we get 1, then the number is odd, which means last bit is set. So we increment the result and we change n equal to n by 2. So what we have basically done is, we have moved the second last bit to the last position, right? Now in the second iteration, we again check the same thing, whether the last bit is set or not. This time the last bit is not set. So we are going to make result as it is. We are not going to increment the result. And we are going to change n equal to n by 2. So and the second last bit goes to the last position now. Now in the third iteration, we check if the last bit is set, our result becomes 2, and then becomes now 0, because the second last bit goes to the last bit position. So we have finally result as 0, which is the number of set bits in 5. Now what is the time complexity? It's theta of d, where d is the number of bits from last bit to MSB. So there are 3 bits from last bit to MSB. So the time complexity is order of 3, right, for 5. Now this solution traverses from last bit to the MSB and then figures out how many set bits we have. We are going to talk about a standard algorithm which runs in time complexity equal to number of set bits. So if you see example of 5, that efficient algorithm is going to run only 2 times instead of 3, right? And if you imagine a big number whose only set bit is this bit, say the most significant bit is at this position, 32th position, if there are 32 bits in the binary representation, right? And say if every bit is 0, every other bit is 0, then this algorithm is going to run 32 times. And the algorithm, the efficient algorithm that we are going to talk about, that algorithm is going to run 1 times. It's basically going to run equal to the number of set bits. Doesn't matter how many zeros you have in between, right? So, and this algorithm is a popular algorithm called Bryan-Cunningham algorithm. Before we talk about the efficient algorithm, a quick note about this implementation. We can replace this expression with this simpler expression, right? The good thing about it is it's using binary operator, right, to check whether the last bit is set or not. And also there's no if condition here. We can simply do result equal to result plus and 1, because this expression is going to be 1 if the last bit is set, otherwise it's going to be 0. We could write this also here, but this is both ways better. It's a bitwise operator and no if condition. Let's now talk about idea for the Bryan-Cunningham algorithm. As I mentioned earlier, we are going to run a loop that is going to run count equal to number of set bits. The time complexity is theta of set bits in the binary representation of given number. So we are going to traverse only through the set bits, and here I have written skeleton of the code to give you an idea. So we are going to initialize result as 0 like the naive method. We are going to run a loop while n is greater than 0. And inside this, we are going to write an expression here. We are going to change n in a way so that the last set bit becomes 0. That's the idea of the algorithm. So if your number is 40, which has 2 set bits, what you are going to do is you are going to first make this set bit as 0, right? And in the next iteration, you are going to make this set bit as 0. Suppose there were 3 set bits, the number was 41, then first you will make the last set bit as 0, then the second last, then the first, right? So we are going to begin from this side and we are going to make all the set bits 1 by 1 0. Now we need to write some expression here so that n changes from 40 to 32 and then 32 to 0. What expression you will write here to make such changes to n? The changes are the last set bit should become 0. Please pause this video and think of the expression for a moment. Here is the expression that will unset the last set bit. And how does this work? Let's say n is 40 and we have this binary representation. N minus 1 is going to be 39, which is going to have all the trailing, in place of all the trailing zeros, it's going to have ones. See, when you subtract 1 from a number, what happens is all the trailing zeros, they become 1 and the last one becomes 0, right? So trailing zeros become 1 and this one becomes 0. Now if you take a look at this, closer look at these two numbers, what happens is if I do bitwise AND of these, this is going to be 0 because there is a trailing 0 here which will make all these ones as 0, right? So if I do bitwise AND, these 3 are going to give you 0 and this one is also going to give you 0 because this was 1 in the original number, now it becomes a 0, right? So when you subtract 1 from a number, all the trailing zeros become 1 and the last set bit becomes 0, and that's what gives us the result that we get the last set bit removed. Now if I do a bitwise AND of these two, I'll get this 1 as 0. Now if I again do the same, 32 minus 1, 31, all the trailing zeros become 1 and this one becomes 0. Now if I do bitwise AND of these, I am going to get everything as 0 because there are no more ones before this one, right? So finally I get the 0 and I get the result as 2. This is how this algorithm works. We are mainly using this expression to unset the last set bit. We are now going to talk about our next solution, and this solution is going to give us count of set bits in big O of 1 time. It's going to use a simple expression to count the set bits, but the idea that we are going to use with the solution is we are going to pre-process the numbers. We are going to assume that we have only 32 bits in the binary representation of the input numbers. We have 32-bit numbers. And with this assumption, we are going to do some pre-processing so that we can answer every count set bit query in big O of 1 time. See, if you have multiple count set bit queries, if you need this multiple time, it's a good idea to pre-process the numbers so that you can give the answer for every query in big O of 1 time. And one solution that you might be thinking is, I'll compute count of set bits in every number, all the 32-bit numbers, right? And such numbers are going to be huge. You are going to have 2 raised to the power 32 different numbers, right? Which is a huge count, and it's not a good idea to count set bit in every such number and then answer, right? The table is going to be really, really big where you are going to store the count. Instead of that, we are going to count set bits for a smaller set of numbers, and using this smaller set, we are going to answer the queries. So for 32-bit numbers, we are going to create a table of size 256 and we'll do some pre-processing in this table so that we can answer every query in big O of 1 time. So you may pause this video for a moment and think, how will you make a table of size 256, right? And you will store certain values in it so that you can return count of set bit in every number or in any number in big O of one time. Here is the detailed idea of table based approach. What we are going to do is, we are going to first pre-compute count of set bits for all 8-bit numbers, which means numbers from 0 to 255. And how do we pre-compute it? We know that count of set bits in 0 is 0. Then we run a loop from 1 to 255. And for every number, we simply use Bryan-Cunningham algorithm, right? We reuse a result for this number, right? This reduced number, where we have removed the last set bit and we add 1 to it, right? You can use naive method also, or I've used Bryan-Cunningham here. In the naive method, you will use table I by 2, plus you will use I and 1. You will check whether the last bit is set or not, right? Here I've used Bryan-Cunningham algorithm. So this is how we compute count of set bits in all the numbers from 0 to 255. Now, how do we use these numbers? See, we have a 32-bit number. For example, n is 13. Its 32-bit representation is going to be like this. The first 8 bits are going to be 0, next 8 bits 0, next 8 bits 0, and last 8 bits with first 4 bits 0 and last 4 bits as 1, 1, 0, 1, right? So we want to count the set bits. So what we do is, we count set bits in this 8-bit segment, then this 8-bit segment, then this 8-bit segment, then this 8-bit segment, right? And we can count the set bits in this 8-bit segment using table, right? So we use table to count set bits in individual segments, and then we sum the count. You must have guessed it, right? So count in this is going to be 3, here 0, here 0, here 0. So the result is going to be 3 plus 0 plus 0 plus 0, right? So the result we are going to get as 3. Now the question arises, how do we get the count in individual segments? What expression we write? So please pause this video for a moment, and you have the table, you have the number, you know the approach. How will you count the set bits in individual segments? To give you a hint, to count the set bits in this particular last segment, what you will do, you will first generate a number, a 32-bit number, which has all the last 8 bits as set. And how do you generate such number? See, this number is simply going to be 0xff, right? This is hexadecimal representation of integers. When you write 0x as the prefix, it becomes a hexadecimal number. And ff means all the bits is set. F represents 4 bits and 4 bits are set here. Or in other words, you can say you simply write 255, right? Instead of 0xff, you can say you have 255. So what you are going to do? You are going to do a bitwise AND of the given number with 255. That will remove all the previous set bits. Suppose it was a big number where you had some set bits here. Once I do bitwise AND with this, because this has all these bits as 0, and if I do bitwise AND with this with any number, its first 24 bits will become 0 and only last 8 bits, whatever they were, they will remain as it is, because we have last 8 bits as set in 255. So that's the idea we are going to use, right? This way we can count in the last segment. Now how do we count in this segment? We make this as last. And how do we make this as last? We use the right shift operator. So I have given you all the hints. Please pause this video and write down the complete code. Here is the implementation of the idea. We have first a table of size 256. I've written C++ style code here. If you're programming in Java, you will write table square brackets, then equal to new int 256, right? And whether you're programming C++ or Java, I have assumed that this table is available inside both initialize and count set bits function. In C++, you can make it as a global variable. In Java, you can make it as a class variable, right? Or that is how you can make this accessible, right? Or you can make it as static and then static methods. That would be better. So what we have done here, we have simply written the same initialize function that I just talked about. Table of 0 is going to be 0. Then from 1 to 255, we are using Bryan-Cunningham algorithm to count the set bits in every number I, right? Table of I is going to be table of I and I minus 1 plus 1, right? We remove the last set bit. So this is initialize function, and it's going to build a table of size 256. For every number I, table of I is going to give us count of set bits in the number I, right? So we begin with 0 for 1, we use 0 plus 1, 1. For 2, we are going to again do the same thing, I and I minus 1, which is going to be 0 plus 1, right? So that is how we compute. Now, what we are doing here, we just talked about this. We consider the number 255, which is all set, all the last 8 bits as set, and remaining 24 bits, the leading 24 bits as 0, right? the binary representation of 255 is this. The first 24 bits are 0, right? These 24 bits are 0. Then the remaining at 8 bits are all 1, right? That's how the 255's binary representation is. So when you do bitwise AND of 255 with n, what happens is the first 24 bits are all going to become 0. In this example, they are anyway 0 in case of 13, but suppose the number was big, whatever set bits there were, they would become 0. We'll get the only the last 8 bits in the given number, and we'll do bitwise AND so that we get the only last set bits, right? That's what happens when you do bitwise AND. Now we have a number which is having only set bits in the last 8 bits, right? Which is a number less than 256, right? And we can count the set bits in such a number by doing a lookup into our table, right? So we do a lookup of this expression in the table. This number is definitely less than 256, and we get the count. And in case of 13, we get the count as 3, right? There are 3 set bits here. Now to get the counts in this segment, although it's 0 here, but suppose the number was big, suppose the number was 250, more than 256, right? So what do we do here? To get the count here, what we are going to do? We are going to right shift it by 8. So this segment comes here, right? And when this segment comes here, you again apply the same logic. And when this segment comes here, this segment goes away, right? That's how the right shift operator works. These 8 bits go away and these 8 bits come here, and the leading bits become 0. So you get the count in this segment. Then you right shift it by 16, you get the count set bits in this segment. Then you right shift by 24. See, in case of 24, I had not done AND with 255, because when you are right shifting by 24 bits, the leading 24 bits are anyways going to be 0, right? Because you are shifting these here. So right shift operator is going to prepend as 0, all the leading bits are going to become 0, right? Leading 24 bits are definitely going to be 0. So we don't need to do a bitwise AND with 255. So we get these 4 expressions. In case of 13 example, we get 3 here, 0 here, 0 here, 0 here. So that's how we get the set bit count, and that works in big O of 1 time.